Okay, today, or actually this week, we're going to be talking about mobile device security. We're going to spend 2 lectures on talking about mobile device security. The lecture today is mostly going to be sort of the platform, the lower levels of the stack. And then on Wednesday, we're going to talk much more about application level security. And so Wednesday paper is an Android paper, and today's paper is the white paper from Apple. One reason for us to sort of take this topic pretty seriously and spend a bit of time on this is that mobile device security is generally better than desktop security. And partly because mobile devices came later, people knew more about security by the time actually the mobile devices came around, and so they did a better job. And so there's interesting things that we can learn by studying mobile device security. Another interesting, in one way, this actually is another case study of enclave support. And we'll see the same abstraction that showed up in the last lecture, where we were talking about running sort of sensitive computations separately from the operating system and not trusting the operating system at all. This shows very prominently up in the design for today too, except it's sort of more hardware implementation of enclaves as opposed to software implementation. So that's the top level. And so maybe the right place to start is to think a little bit about what the threat model is. The document that we read for today is quite extensive, covers a lot of different topics. But at the core, what is the threat model that is being assumed? And so the threat model actually is relatively straightforward, if you will, or easy to state. Basically, the issue that we need to consider, or the attack needs to be considered, is that the attacker steals the phone. And wants to read the data. So the scenarios are like you leave your phone behind here, and you might want to, you're worried that maybe after you lost it, that somebody else would read the data. Then Apple wants to protect against that. And to make that plan happen, they have to make some assumptions. Then it can't be arbitrary stealing and reading. There's some assumptions that they have to make or will make. One is phone is locked when the device is stolen. Like if the phone is not locked and the device is stolen, then of course the attacker has this full access to your phone. And so there's a starting assumption is that the phone is locked at the point that it is being stolen. And the second is that it is password protected. If it is locked, but there's no password protection on it, or there's no protection or Face ID or whatever protection at all, then of course the attacker can just unlock the phone and read whatever is there. Right? So that's sort of the 2 starting assumptions. The phone is locked when it gets stolen, and it's password protected. Under those 2 assumptions, basically what they want to guarantee is that even if the attacker steals the phone, has physical access, has the phone in his hands, the attacker can still not read your data or your files. Does that make sense in terms of the threat model? So, even though the threat model is pretty sort of straightforward to state, you can see from the document, it actually takes quite a bit of machinery and effort on Apple's side to try to deliver on this, defend against this particular threat, right? It's a quite of extensive engineering and design effort. And so you may wonder, why care? Why put so much effort into this problem? Now, it's quite harsh to speculate, exactly why. I don't really know exactly why Apple cared so much about this problem, but there are a couple of reasons why, that seem very plausible, right? There are customers. There are customers who must keep secrets. There might be customers or companies that have medical data or financial data or reporters that store confidentiality in their phone, and they're customers of Apple, and Apple wants to give them very strong security. And maybe even by law, they're required to actually to be able to use the device, it must have a strong security plan. Second, there are presumably ordinary customers. When they log into their bank, they want to have some guarantees that the password that they use to log into their bank actually is protected, and cannot be easily stolen by an attacker once the attacker steals their phone. And so that seems like a reasonable thing to want. I think there are two other reasons. One, I think Apple thinks this is a competitive advantage. If the phone has a better security plan, can deal with this particular threat model, maybe more customers want to buy an iPhone. And I think finally, there's some element of just trying to do the right thing. Which presumably is good for Apple's image. So what are kind of attacks should we worry about? Right? I mean, I stated what can the attacker do once he steals your phone? And if you go and comb through the document and you start making a list of all the particular attacks they consider, you get a list sort of like this. The first and obvious one, correct, is somebody actually does an exhaustive password search. The attacker has physically access to the phone. Most PIN codes are pretty short, like 4 digits or something like that. And so in principle, the attacker has to try out very few combinations and could actually log into the phone, correct, and that be violating our goal. And so there has to be some plan to limit the number of password guesses to ensure that an attacker can't really break your password or get access to the phone. Similarly, along the same lines, they worry about somebody impersonating fingerprints or face IDs. So they've got to have some story for that. They worry about an attacker removing the flash card or flash chips. And the particular attack here is that the flash chips contain your file data. They worry that the attacker may open the phone, take the flash chips out, and stick them in some other phone or some other piece of hardware and try to basically read the data from the flash chips directly. Other things they're very worried about are bugs in the kernel. iOS, which runs on your phone, is a big piece of software. Has a lot of system calls, a lot of code, so presumably there are bugs in it. And they're worried that the attackers might be able to exploit those and maybe get around the limit on the number of password guesses, or be able to impersonate fingerprints because the OS stored a fingerprint from previously and replays it. So worried about that. And not just bugs in the kernel, but also like maybe as least important or important to call out separately, bugs in driver software. Because even when the phone is locked, the phone actually is maybe running applications or is talking over the Wi-Fi radio or whatever. So there's a bunch of code still running even when the phone is locked. When the phone is locked doesn't mean that the phone is off. And so they have to be worried about like maybe an attacker can tickle a bug in one of the driver pieces of software, and that way can get control over the device. And finally, of course, they have to be worried if the attacker has physical access to the device. Maybe the attacker can arrange to basically boot his own operating system on it, right? And then the attacker is free and can do everything he or she likes. And so they have to worry about how to ensure that actually the appropriate software is running on the device, in particular, so this is some form of secure boot, in order to ensure that the device actually runs the Apple software, so that the attacker doesn't really can install its own operating system, or not only installing its own operating system, maybe if that is going to be hard, the other worrisome is maybe the attacker can roll back an Apple operating system to like a while back, and that version happens to have well-known bugs that the attacker could exploit. And so the other attack that they worry about is actually an attacker downgrading or rolling back to a previous version of the operating system, their own operating system, the Apple operating system. Okay, does this make sense? We understand the threat model. We understand the potential attacks. Okay, good. So one thing to point out, maybe before sort of diving into more detail, is that 10 years ago, before sort of this all happened, it was reasonably easy. None of these mechanisms that we're reading about or read about today were around in the phones, and it was pretty easy to steal, and for an attacker, once you have physical access to the phone, to actually steal the data off the phone. And with the measures that are in this white paper, described in this white paper, it's now incredibly much harder. And in fact, they have done a pretty good job, actually protecting against all these attacks that we just listed here on the whiteboard. And as a piece of evidence, that is actually they've been reasonably successful is that the FBI has been complaining about it, right? They have had phones where they would like to read the data off the phone, and they cannot, or it's very expensive for them to do so, and they have complained to Apple and say, like, please install a trapdoor, in your operating system so that in the future we could actually read things much more easily. And it's well known, a couple of years ago, Apple just refused to do that. But it gives you a sense that this is pretty strong security, right? Okay. So let's look in a little bit more detail and try to understand how it works. So we'll just take a little bit of a hardware overview. And hopefully this picture will help a lot in trying to understand how all the different mechanisms relate to each other and help in achieving the goals that we here have on this board. So there's a regular main CPU, and that talks to some DRAM or some memory. And this is like your standard chip, your standard processor. This is the processor that's going to run iOS, runs your applications, interacts with the UI and all that kind of stuff. So this is the processor where most of the code runs. And in addition, it's connected to two different other pieces. It is connected to some sensors. So for example, a fingerprint sensor or a Face ID sensor. And then on this side, it's connected to there's a second sort of chip. I'm going to draw it very big, even though it's probably smaller compared to the left side. And this is the secure enclave chip. And in the goal is going to be that what we want to do is arrange that basically all the sensitive computation, the sensitive code runs inside of the enclave. And basically the code that we don't want to trust, we let that run on the main CPU. So the idea is here is like iOS and all the applications will run here. And the code that is sort of necessary to defend against these particular potential attacks, runs inside of the enclave. And so there's a separate processor in here, the enclave processor. And the enclave processor, of course, needs to start from somewhere and needs to have some information to get going. So it actually has a little bit of its own ROM, read-only memory. We'll see exactly what will be stored in that, but that's basically where the enclave processor starts from. So when you turn on the phone, you have to run some code. That code must be secure in some sense or another, because if it would be the wrong code that we started with, then we basically we're sort of in a bad place right away. But it boots therefore from its own memory that is inaccessible from the rest of the phone. Inside of it, and this is probably the most interesting aspect, there is a key sort of burned into the hardware, which is called the UID. And this is I think a 256 AES key. Right? And so this is when this chip was made. This key was fused into the silicon itself. And nobody can actually really read it. Nobody can write it. Not even the secure processor can actually read it or write it. The only thing you can do is actually you can ask to decrypt or encrypt data with that particular key. So you can ask the silicon, please, encrypt some data, with the key that I can't see. And that key can be fed into an DMA AUS engine that sits between the main memory and flash chips that contain the user data. And the idea is being that whenever the operating system wants to write your files, those files, or when the data is written back to the file system, that data is immediately encrypted with some set of keys that are managed by the enclave processor. And so the operating system itself that runs on the main CPU, iOS, has no access to these keys. Only the enclave processor or the enclave chip, the secure enclave area, has access to this chip. And this guarantees that basically as the data flows basically from memory into the flash, the data is always encrypted with the keys that are set up by the secure enclave processor. And the basic idea, correct, is that now you can't really look at the data that's inside of the flash and deduce what's in it, because actually the data is encrypted. So this is going to be encrypted storage. Does that make sort of sense? And so in some sense, going back to last lecture, this picture looks very similar, correct, in some ways to the enclave picture that was last week on the board, where we have the untrusted operating system. The picture was drawn slightly differently. We had the untrusted operating system, and on top of that, there was an enclave. Correct? And the enclave could run sensitive computation, even if the operating system was malicious. And the setup is here very similar. We have although the operating system is written by Apple, they're going to assume that the operating system might be compromised. And all the sensitive things that are actually really crucial to security and again defending against these attacks, that code is going to run here. And so even if the operating system is malicious or overtaken by under control of the attacker should not be able to basically read, for example, your data from the flash chips and decrypt it. Does that make sense? OK. So that's sort of at a high level, what the picture looks like. And there's a bunch of interesting aspects to the design that I want to go in a little bit in more detail. And then it will help us understand how they defend against the attacks that we got here. So one important part is secure boot. So we're going to talk about that in quite a bit. And what this will do, it will establish, or it will arrange, there has to be some plan, basically, for Apple to make sure that when this phone boots and turned on, that actually the secure enclave processor actually is running Apple code, that was written for this particular enclave processor, and not code that was basically supplied by the attacker in some way or another. Because if the attacker had control of the enclave, of the code running in the enclave processor, it would be game over, right? So secure boot must be an important part of the story, why we're going to be able, hopefully, to be successful. Then another important issue is like how to do this division. What should the operating system do, and what should the enclave processor do, right? And so what exactly the enclave does is going to be important. And so, for example, just the one thing we can have to assume, basically, that has to be true, correct, is that the enclave processor is presumably responsible for user authentication. If you type in your PIN, it better be the case that that PIN actually goes to the enclave, that the enclave does the limit on guessing, or limits the number of guessing, and that the operating system really doesn't get no hands at all on your PIN, right? Because if the operating system got also the hands on the PIN, maybe they could replay it to the enclave, right? And so there's got to be a little bit of good plan to make sure that basically the I/O path, from the user, correct, to the enclave is in some way protected, and that the enclave, does this enforcement of the guessing. Okay, so there's got to be a bunch of interesting things around, like exactly, what this code all does here, and how to limit that code, correct? Because we want to have as much, not that much code there as possible. And then finally, what we're going to see is it turns out that the data encryption part is also actually quite interesting. I made it out to be here as being reasonably simple, correct? There's a key that's set up by the enclave processor, stuck into the AES engine, and then data is encrypted on the file system. We're done. Well, it turns out the story is more complicated, because even when your phone is in log mode, and presumably, hopefully, some of the key material that actually is directly related to you is destroyed, as we'll see, there are background applications that may still have to have access to your files, or at least to some of your files. And a prototypical example that's mentioned in the white paper a couple times is you might be downloading email attachments in the background. And it would be very nice if that still works. Right? And so there has to be some story for that, and that actually makes the whole data encryption story slightly more complicated than the base story. Okay. Questions before I dive into any of these three topics? I'm going to go one by one. Okay. Let's talk about secure boot. So when the phone turns on, it basically starts running some piece of code that actually is stored into the ROM. So you draw a picture, and what we're going to see is that basically booting is going to take a whole bunch of steps. It's not one step. In fact, there are many, many bootloaders running one by one before actually your first application runs. And so the first thing that actually runs is actually the boot ROM. So the ROM is read-only. It's burned, the code is burned into the ROM at manufacturing time. And when you press on/off, basically the programmer counter starts running at some set of instructions that sits in the boot ROM. And that code is clearly very fixed, correct? And so presumably, the first question you might wonder, like, why is there any more stages to booting than that? Why don't we just stick all the code for booting into the boot ROM and then we're done? And why do you think that might be not a good plan? Yeah. Yeah, you can't send out updates anymore, right? And so you don't want to burn basically iOS into the boot ROM, because then you couldn't update iOS anymore. And so you have to have sort of a multi-stage process. So that's exactly what's going on here. The boot ROM basically boots the next bootloader, which is called iBoot. But before running iBoot, that sits somewhere in memory or somewhere in the flash chips, we got to make sure that actually that is trustworthy code, right? Because if we just like blindly start running some code that sits on the flash chip, maybe the attacker installed that code, and we'd be in serious trouble. And so, in fact, what actually happens is the boot ROM has a couple other pieces of information burned into it that can be accessed, which is namely Apple's public key. Sits in the boot ROM. And so when the computer starts, or your phone starts, the bootloader starts running, executing instructions, but it has access to Apple's public key. And Apple's public key is completely public, right? So anybody can read it, it's perfectly fine. Yeah, go ahead.
Apple's public key is fixed. Does that mean that if Apple's private key were to be leaked by an attacker or something like that, that means that all of the phones would be?
Yeah. So this is a very good point. I mean, at the end of the lecture, we'll come back and sort of talk about what is the attack surface that is left after implemented all these measures. A number of you asked, like, wow, this is pretty impressive. Like, how do you actually break into the phone? Is it still possible or not? The answer is still possible. Like everything in this class, correct? Every security plan, in the end, can be broken in some way because there's not really anything like perfect security. It's always a cost trade-off and performance, usability. And so also in this case, there are attack surfaces. And one of them is steal Apple's private key. So if you have an attacker, you could steal Apple's private key, you're in business, right? Because you can upgrade anybody's phone, to run any hardware you like, any software you like, and you're good. So should we stop reading the white paper? I didn't put it on it's not on the list of attacks they consider, correct? We're going to talk about it later, but on the list of potential, this is not the one they're worrying about. Why are they not worrying about that one? It seems like the first one you brought up. Yeah. It's presumably the first thing the attacker thinks too. What do you think? It's like, is this a serious problem or minor problem or game over? Clearly it's not game over, correct? Because otherwise the FBI would have done that too. So, yeah, go ahead.
They probably just have a giant secret key.
Well, presumably they do. They presumably, that's a well-chosen, very good, private secret key. Is it stored online? Maybe not. Probably air-gapped, correct? And so presumably Apple has, this is not part of the white paper, and I don't know how it works, so I can't tell you, but I can guess, or you can guess. It's probably very well protected, correct? And most likely, it's actually not sitting on the internet or any computer that's directly connected to the internet at all. It would be highly dangerous if that were the case, right? And we'll see this later up, showing up in a bunch of other places in the semester where when we talk about server certificates, there's a similar issue. Like, where is the server's private key stored? And in most of the cases, the answer better be not on the internet. And so I think that's the case. They don't really describe it, and I don't really know, but that would be my guess. There's a very serious protection scheme around the private key, and so any signing that's done with the private key is probably done on a computer or a set of computers that's actually not connected to the internet. Okay, good question. Oh, yeah, so let's assume for now that the private key is not compromised, and only Apple has the corresponding private key for this particular public key. And so what actually happens, this boot code, will find the iBoot code, and the iBoot code is actually signed by Apple's private key, with Apple's private key at some point. And when before the boot ROM actually starts running iBoot, it will check that signature and see if indeed the signature checks out using the public key. And if the signature checks out, then presumably there's some confidence that the code that they're starting to run is actually code supplied by Apple because it was signed by Apple's private key. And if we did a good job, if Apple did a good job of hiding or keeping that private key secure, we might have some high confidence that actually we're running Apple code, right? So that's the iBoot. And so it checks the signature. And that turns out sort of be the basic plan. Like every piece of code that runs after this, the first thing it does before starting a new piece of code, it will check whether it was signed with the Apple's private key and make sure that signature checks out. And so in fact, the next thing, so iBoot actually what it does, it programs some of the sensors, starts them up, and sets a bunch of other things up. And then it actually boots the kernel that runs inside of the enclave processor, the enclave kernel. And it does exactly the same thing. It will find the code for the enclave kernel somewhere. It will check the signature on the enclave kernel. If the signature checks out, then it will boot the enclave kernel. And so at that point, basically the sort of machine is operational. Right? We got some sensors up and going. We got the enclave processor running the enclave code, and it's all Apple code. All right? So then there's a couple more steps, and that basically, those are the steps to actually get the main CPU to run. Right? We're not running iOS yet at all. And so the next couple steps typically are for, basically there's some UEF code, standard for booting, and that actually will go off and boot iOS, and that will actually boot your applications. And this, from here above, runs on the enclave. And here, this runs on the main. Okay? Does it make sense? So basically, when the machine or your phone is up and running, and if the signatures have checked out, we might actually have pretty strong confidence that all the code that actually is running on the phone actually was code that was produced by Apple at some point because the signature's checked out. Okay? Yeah? Sorry?
What is it checking the signature out? Like, what is signed by Apple that you're checking?
Yeah, so the whole, everything that's necessary to basically to run that particular piece of code. Right? There's everything that's relevant to actually making sure that the machine does the right thing has to be in the signature. So presumably this completes the complete binary of the kernel, all and the whole block, whatever how big it is just signed with the signature for that is checked. We'll talk about it in a second in a little bit more detail. Yeah.
You had a question?
Good.
Why can't we make desktop security as secure as mobile device security?
So everybody heard the question. So why actually is desktop security not as good as mobile device security? Well, this is an excellent question. What's the answer? Yeah, go ahead. You're in the middle there.
Desktop security has to do with a lot of legacy or existing code to make sure that it works with a lot of kernels and whatnot. And there's just it's older, so it's just more buggy.
Yeah. I think another answer here. Yeah.
Mobile devices are more predominantly like closed ecosystems, like Apple controls this entire device, whereas Windows, like Microsoft, might not be able to control. There might not be a TPM or like a secure enclave on every computer.
Yeah. So I guess both reasons are totally valid reasons. One of the nice things about the mobile device world is that basically they got to start from scratch almost, right? So 10 years ago, and there's no code that really had to run. It was a clean slate design in some ways, and as a result, by the time they started doing that, we knew, or the community as large knew a lot more about computer security. And so they could take advantage of all the lessons learned from all the bad things that happened to desktop security. All right, so that's one reason. The second is indeed the desktop areas or setup is much more open. And there's much more standardized, and so there's no one operating system, there's no one hardware platform, it's not all made by the same manufacturer. And so things like this are much harder to pull off. People trying, and it's not like a lack of trying. The other thing I think that's going on here is the threat is much more serious here, correct? You know, your desktop's getting stolen is probably something you worry might be slightly less about than your iPhone being stolen, correct? Presumably your desktop sits somewhere in the room locked in a key, and you don't see a lot of people running over your desktop, stealing your desktop and going somewhere else, correct? So it's just like not as portable as an iPhone, and so for an attacker to get hold of your iPhone is much easier, correct? And also much more plausible. People leave their iPhone on a table, go to a restaurant, leave your iPhone by accident. Be nice if your data doesn't get stolen. It's unlikely that you leave your desktop lying around in a restaurant after dinner or something. All right? Does that make sense? So maybe no really fundamental technical reason, what that explains the difference, but mostly a question of evolution and actually now a much better understanding about like how you could build secure computer systems. And this is one reason why we picked this, we're looking at mobile security. Yeah?
How does iBoot check that the entire OS kernel is signed by Apple? Because there's a lot of code in the kernel.
We'll talk a little bit later. I guess this class is not really about crypto, but presumably what is going on is you first compute a cryptographic hash over the code, which reduces whatever the megabytes of code to a short byte string or bit string, and then you sign that bit string. And so when you check, what you first do is you take the code, you recompute you validate the signature, and you'll get the valid hash out of that, and then you can recompute the hash, cryptographic hash for the bits you have stored and compare it to the cryptographic hash that was in part of the signature. Yeah?
If someone was to install a malicious kernel on an iPhone, is the phone essentially wrecked for the rest of its existence?
Yeah, that's a good question. Like, what happens when the signature doesn't check out? Something must happen. Anybody pick that up from the white paper? That's a great question. Yeah.
You got to connect items, sort of, right?
Yeah, you go into, I think it was called, I don't actually have an iPhone, so I don't really know, but I think you go into recovery mode in the same way as your Mac goes into recovery mode. And then you basically can do a factory reset or go through iTunes and maybe get your correct software installed again. I don't exactly know, but basically you end up in the recovery mode screen, and then from then on it's your job to get back the machine in order. In the worst case, just a factory reset and then start over again. All right? Good. Okay, so after this, we should have reasonable confidence, that we're running, Apple software, and so the problem left is there's still sort of a problem left. Namely, we might not be running a recent version of the Apple operating system, right? And the really particular problem they worry about is a downgrade attack. And so the basic idea here is that the attacker gets hold of an older version of the software, which is signed with Apple's private key, so it's like it's valid Apple software. The attacker stores that on your iPhone. Now your iPhone is going to boot this old Mac OS, iOS version of the old version of your software, and maybe that old version of the software actually has bugs that are well known by the time that the attacker actually, because it's an older version, bugs have been found, they've been fixed, but they're well-known bugs, and the attacker maybe can use one of those older bugs then to basically take over your iPhone, right? Does that make sense? And so what do they do against that? Well, it turns out they have the following plan. In addition to Apple's public key, there's another piece of information stored basically in this read-only memory, which is called an ECID. And this is a unique identifier, or 64-bit number that basically identifies your phone uniquely. If you look at, if you go to your phone setting, at the bottom, you'll find, somewhere also the ECID, for your phone. And to protect against they use that ECID in their downgrade protection attack plan. And the outline, there's not a ton of detail in the white paper, but the basic plan is roughly on the following lines. So here's our phone, here's our iPhone, and the user decides, they want to upgrade their iPhone. And so what is going to happen is it's going to send actually a message, to whatever Apple Central. Here's this Apple. And in that message, there's going to be the ECID, some nonce for replay detection, and what I call measurements. And the measurements are basically what I talked a little bit earlier about, are sort of the cryptographic hashes of the version of the software that the iPhone wants to install or to upgrade to the next version. And then a couple things happening here at Apple. Apple looks at this ECID, which is unique per phone, and basically checks what is actually the current software that you're running. What's the last time you did an upgrade for that particular phone, and they know basically from that what version is the latest version for that particular ECID. And so if you ask for a software that is older than that version, they know they should not supply it to you. Right? So the only thing you can do is basically you can get newer software, but not older software. And so what they send back, roughly, again, the details are slightly vague, what they send back then is basically a message that contains the measurements, the ECID, and the nonce, all signed with Apple's private key. And so when the software on the other side receives it, it will check, that the signature checks out. If the signature checks out, we'll check the ECID if it's indeed, the measurements for its phone, that the phone is being upgraded. And we'll check the nonce just to make sure that this is not, something that was an older version. The attacker recorded this like a year ago and then replays it. And so basically, if all this stuff checks out, then do the upgrade. And the reason why this is a good scheme, or at least improves security, is that you can't now take, for example, let's say you have an iPhone, and basically his iPhone runs behind, and what I want to do is basically take the software on your iPhone and basically boot it on your iPhone, correct? Because then I can sort of implicitly launch a downgrade attack. This is not possible because the ECID is being checked. Like when your phone wants to do the upgrade, it's going to say, that ECID doesn't match the ECID for you, so therefore I'm not going to do that phone. So basically you can't take software that was running on one iPhone and run it on another iPhone. Second of all, because of the nonce, we saw this before, correct? This is one unique identifier that's basically used against replay detection. We saw this in the UTF protocol too. That basically ensures that the attacker can't record this and then replay it a year later because it will have an old nonce that the iPhone is actually not expecting. Does that make sense? So basically, this sort of ensures that really you can't only get more newer versions of the software on the phone, and you can get older versions of the phone, software on the phone. Yeah.
Store the version number in like encrypted storage?
Yeah. Why this scheme? Why don't you just stick a version number and stick it somewhere on the phone? That seems like an alternative great plan, right? I mean, like maybe just the first thing you would think of, basically store the version number in Flash somewhere, right? And then check against that version number. Yeah. Yeah, I think this is exactly right. They're worried that the attacker might be able to change the version number in some way or another. Maybe not completely obvious how you would do that, correct? Because presumably you need to access some key that allows you to change the data. So this might be slightly complicated, but presumably, that version number sits somewhere in memory, and so maybe you can change it. Right? Yeah.
If you can change the version number, can you just change the ECID and issue false requests to Apple server?
Yeah, good point. So, yeah, why not change just the ECID? Yeah.
Isn't that like part of the processor?
It's part of. It's not like the UID, which is actually a little fused into the processor. I think basically the answer to that question is it's unlikely the attacker thought far ahead in advance that he wanted to do a downgrade attack on a particular phone that he saved that response from much earlier from a year ago. So I don't think this is a bulletproof scheme, but very hard to actually pull off, because that means like if you want to break into somebody's phone and you want to do a downgrade attack, you should have recorded that message a long, long time ago.
You just have your own version and put your ECID there.
Well, okay, so the ECID sits in the boot ROM, so you can't really write it, and it has to be read by the boot. And it is done by the enclave processor, and the enclave processor is running Apple software, correct? So we're starting the assumption that there's some good software running. We're only worried about like downgrading good software to bad software. Okay. Good, so that's secure boot. That all makes sense? Okay, let's, the next topic. Let's talk a little bit more about the enclave. So the enclave manages basically all keys. And is responsible for limiting password guessing. Another way of saying this is that basically it's sort of the central, it is the piece of code or one of the central functions of the enclave is to do user authentication. So why can't we trust the main CPU to do user authentication? And what bugs are they worried about that? Or what attacks are they worried about that they don't want to outsource that to the main CPU and they sort of insource it to the enclave? Yeah.
If there's like a kernel bug or a kernel compromise, then you have access to the whole system, including authentication.
Yeah. Yeah, so the key concern here is that if iOS were doing the user authentication, then if there was an exploit in iOS or a bug in iOS and the attacker could take advantage of, then the attacker is in control over user authentication and, for example, disable the limiting on the password guessing attacks, and that way, can get hold of all the data that sits on your phone. So it's crucial that that cannot happen, and so therefore, this is actually all done on the secure enclave. This is a very sensitive, security critical piece of the plan, and so it's done on the secure enclave separately from the main CPU. Okay. So there's a couple interesting aspects to make this work, right? And one aspect that is very interesting is that notice that the sensors, sitting on this side, right, actually connected to the main CPU. And so the sensor is the thing that reads your fingerprint, or whatever you're typing your PIN code, or the Face ID, and that data, correct, from the sensor flows through the main CPU through the memory to actually the enclave processor. That seems like a bad design, right? Because what could happen? Well, for example, we had another kernel exploit, and basically we were running a buggy kernel or a compromised kernel. Are we in serious trouble? Yeah, go ahead.
Like if it's a fingerprint sensor, it can like store the fingerprint that was recorded the first time and then replay it later on, maybe?
Yeah, right, exactly. The operating system, if it was compromised, could maybe record the fingerprint for a while back and then replay it later, and then maybe get access and then unlock the phone, right? So this seems like a little bit of a problematic, and so indeed, they actually have a really sort of interesting story for that. So the sensor to enclave communication is actually protected. It turns out, the way they do it is they have there's a shared secret or shared cryptographic key shared crypto key between the enclave and the sensor. So in fact, at manufacturing time, when your phone is actually produced, there's basically a shared key here, say a key sensor, and the enclave processor also has access to it. And that key is used to basically set up a cryptographic or secure communication channel between the co-processor or the sensor and actually the enclave processor. So basically what happens, you can think about the sensor, it also has a little bit of a, not a general purpose processor in it, but it has a little bit of a computing engine in it. And it reads, whatever, the sensor data, and then encrypts it and signs it with this key KS, and then sends it, through the untrusted, main CPU and memory system to the enclave processor. The enclave processor has the KS and can just basically verify the integrity and the confidentiality of the data that's inside of it, and decrypt the data that's actually that the sensor sent to it. Right? So the operating system, doesn't get actually, gets to see the encrypted version of your fingerprint, but can't actually see the fingerprint itself. Does that make sense? So this is pretty sophisticated, right? Like the sensor actually, does cryptographic operations, has access to keys, and there's all special purpose hardware produced, for your iPhone. Yeah, question. A very good question. So the question is like, how does this protect against replay attacks? Now, presumably, there's some nonce to, there's a real cryptographic protocol. And we'll talk a little bit about this later when we talk about how to set up a secure channel. Particularly, so think about this. Think of have the following simplistic model in your head. Basically, the sensor sets up an SSL connection or an SSH connection up to your enclave processor and talks over that SSH connection to your co-processor. And later in the semester, we'll talk about actually how to implement SSL or SSH or any form of sort of secure communication channel that both does protection against confidentiality and does integrity checking and ensures freshness. But there's a whole cryptographic protocol, presumably that's there. The paper doesn't describe it, but that has to be the case. Okay, good. So now, so basically we have a secure way of sending whatever PIN or fingerprint basically to the enclave processor. And now the enclave processor, of course, can actually enforce any guessing limit, right? And the paper talks quite extensively about it. What happens if an attacker tries to guess 10 times and gets it 10 times wrong? It wipes your phone. Right? And so the data basically, the enclave processor, presumably what it will do, as we'll see in a second, basically erases the keys, and it is not possible anymore to actually read any data from your phone. And so the attacker has a very limited budget to actually, basically for guessing. Does that make sense? So a lot of people asked about the Face ID and fingerprint ID, and so like, only one out of, what was the number, 1 out of 50,000 or something like that? That sounds terrible. Is it really that bad? Why is it still probably pretty fine for security? Yeah, go ahead.
After like a number of biometric attempts, it will revert back to passcode.
Yeah, you only get also the same way as password, you only get a few number of attempts, and then you actually have to type in the passcode. And so even though it's not super unique, it's unlikely you're going to get it right in 1 or 2, or the attacker is going to get it right in a few attempts. All right? Yeah.
So Apple claimed that by using the fingerprint or like the Face ID, it allowed the user to have like a stronger password because they didn't have to enter it as often.
Yeah.
Do you think that's actually true, or is it actually like less good passwords because they never have to use it?
Oh yeah, what do you guys think? Who has an iPhone? Good, good. Who has actually the Google phone does the same thing now, so it doesn't really matter if you have an Android phone or an iPhone. But so what do you think? Yeah.
I personally like that my pen after reading this paper.
Sure, you're like?
I like that my pen after reading the paper because I realized it's like really practical.
Okay, so you learned a lesson for. So what do we people think in general? So what do you think?
I think like the theory was good, but I don't think in practice people actually choose good passwords. Like I think it's less secure basically.
You think
Because
it's less secure?
they rely more on the thumbprint in the face as the primary identification, whereas Apple is thinking that this is more of like a secondary form of a password, which is the main point.
Yeah, okay, so I think the real story is that for anything that's really, really security sensitive, like, you actually have to type in your password. And so that suggests that Apple thinks that the password is the strongest thing, right? And I think the fingerprint is there to make it convenient for users to lock their phone. I think they want to encourage users to lock their phone. And if you disable the phone, and you're worried, I think, that if you have to type in your password endlessly, which is much more inconvenient than sliding your fingerprint across the device, that you won't actually do automatic locking of the phone. And if you don't do automatic locking of the phone, the whole starting assumption was that you're only going to be able to actually provide data protection actually if you do lock your phone when you're not using it. I think that's one of the primary reasons. So I think password protection is the stronger one of them, and the fingerprint and the Face ID is there just to encourage you to actually have a strong password and actually using it and have the phone be locked when you're not using it. All right? Does that make sense? Yeah.
Someone asked, is there a system for iPhone recovery?
Well, the phone goes into recovery mode. And then I don't exactly know what happens in recovery mode. Maybe it's a hardware reset. Maybe you can actually reboot, recover from iTunes. If you have a local, have a recent backup of the whole system. But I don't really know any of the details. Yeah.
It's like, what if you forget your password? Then you're just locked out forever, basically.
Yeah. What happens if you forget your password? Anybody? That's a good question. Are you out of luck? You're out of luck. So don't forget your password. Or your PIN. No, you're definitely out of luck. There's no way to recover from that point, other than do a factory reset and go through the recovery mode operation. Yeah?
After the 2016 with the whole FBI backdoor kind of
Yeah.
thing, a lot of companies popped up to try to create kind of like a black box that you can plug into the phone and is able to get around Apple's like password limitations. Do you have, and can kind of brute force after that. Do you have any idea how those companies were able to do that?
No, I don't know. I don't know if anybody else knows. I mean, often the students in the class that know more about particular things than I do. So nobody. So no, I don't. I'm unaware that actually it is possible to easily get around the limits, the guessing limits that are actually enforced by the enclave processor. Okay, good. Okay, so that's login and user authentication. And tied to user authentication is also encryption. So I want to talk a little bit about that. In particular, the thing that we're going to be worried about is, protecting the user key, right? There has to be a reasonable good story for that, because the assumption is that when the user locks the phone, they basically want to set up it in a way so that once you lock the phone, basically the key that's being used to encrypt and decrypt your data, or your most precious files, is not present in the phone at all anymore. So if the attacker gets a locked phone, basically they want to set it up in a way that the user key has, it has been erased. And at the point that the phone locks, the first thing that the phone does when you lock is erase that user key. And that will ensure, correct, that if there's data, your files are encrypted with that key on the flash storage, it's going to be very hard to decrypt that data because the key is not even floating around anywhere in memory, not even in the secure enclave processor. And so the way they do that, okay, so first another point I should make is, so they want to erase the key, but that raises a challenge, correct? Because once you unlock your phone, the key has to come back into existence because otherwise you couldn't read and write your data. And so there has to be some plan, for that to do so. And the plan they have is basically make the user key dependent on the password or in the PIN code. And the particular scheme they use is as follows, or in terms of outline. So the user key is some function of encryption using the UID. Correct? So the UID, correct, was that key that was fused into the silicon. And they encrypt that. And in fact, let me start at the end. I take the UID, take the password, and encrypt that. And then you do the same thing over and over. So you take this, encrypt it, encrypt it, encrypt it, encrypt it, and you do it a bunch of different times, and that produces the actual key. And so there are two things that are important here, correct? The key is dependent on the password. Right? So only a user that actually has the user password can actually generate, the enclave can generate the corresponding correct key. And the second of all, the key is dependent on this UID. Right? So what does that mean? Well, that means, for example, as we talked a little bit earlier about, you can't take the flash chips, stick them in a different phone, and then type in your user PIN and be able to actually read the data, right? Because if you did that, you stick the flash and chips in a different phone, that phone has a different UID fused into the chip, in the silicon, and so therefore you're going to produce a different key, and therefore you can't actually read or write the data in that, on the flash chip, right? So this basically couples the flash chip to your phone. It's like not possible to take them apart. Well, you can take them apart, but you're not going to get any advantage of it. Does that make sense? Why do they do this like many times? Anybody pick that up? Yeah. Yeah, take it longer. Correct? We talked a little bit earlier about it, and it's also part of the lab, correct? Where you don't want your you want to enforce that it takes a bunch of computation to actually guess a particular password or to construct the key, and that's the mechanism they used. Right? Good. Does that make sense? So we got two good properties, correct, out of this scheme. That the key doesn't have to be in the phone when the phone is locked, but the key is also tight, to the particular phone, so you can't take out the flash chips, and sort of brute force somewhere else. Unfortunately, there's a slight challenge, and this gets us into data encryption. And that is background applications. So they want to make it possible that your iPhone runs applications even when the phone is locked. And for example, draws alert messages on your screen when actually a phone call comes in, or download email attachments in the background so that when you actually unlock your phone, actually all your email is there. And there are many examples why they want to run background applications. But those background applications presumably have to have access to your data. At least, like for example, the email attachments comes in, it has to be stored somewhere, and you still want to be protected too, right? But you can't, at the point that the phone is locked, the user key that was used, that in principle, in the sort of naive plan, was used to encrypt and decrypt the data, is not on the phone at all, right? And so that wouldn't make, it wouldn't work. So there has to be some plan for allowing sort of other applications to read and write user data without actually giving the user key, to those applications. We don't want to give the user key because that's very sensitive, correct? That is very precious. And so the plan they have, and this is sort of a reasonable standard trick, is to do something that's called key wrapping. And the idea basically is, the core of the idea is you take one key and you encrypt it with another key. And so, for example, the idea is that, maybe and the reason you want to do that is because you want to delegate, for example, this key 2 to somebody else. And the way you do it is, if you and I share a key K1, I can cook up a key K2 and give it to you. You can decrypt it, and then you actually have access to that particular key. And so that's sort of the basic delegation plan. And I use this delegation plan very aggressively. So you have whole chains of key wrapping to actually make this work. So let's look at a little bit in more detail how this works. Let me see where okay, I'm done with secure boot, so I'm going to erase this. So the topic here is file encryption. Okay, so the first thing they do is that there's a key, there's a top-level key, if you will, one key per file system. KFS, I think, in the document. And this is the basic key. So there's going to be some file system sitting on flash, and when the machine boots, it turns out the whole flash chip is actually encrypted, and the file system metadata, just like where are the files located and all that kind of stuff, is all encrypted using that key KFS. And the basic idea is that, when the system boots, the enclave processor sort of sticks that key into the DMA engine, so that when the operating system reads and writes, it can at least read and write, the metadata of the file system, so that it actually can get off the ground. For example, boot iOS. And that key is sort of generated once in the beginning, for a particular file system. And the enclave, what it stores while your phone is running, it actually stores an encrypted version with the UID of this KFS. So the flash chip itself, even in its memory, or the secure enclave in its memory, protects this particular key by encrypting it using the UID. And why do that? Why? Seems like an almost extra, security measure or precaution. So one reason they're doing this, there are a couple of reasons they're doing this. One, of course, you don't want to take the flash chips and put them in some other iPhone, and be able to extract. It makes it hard, since the key is actually encrypted with the UID. It actually is very hard to actually take the flash chips again, take them out of the phone and put them in some other phone, because you're going to you cannot decrypt its KFS and actually use it to decrypt the files on the flash chip. The second reason they're doing it is sort of a cheap way of doing erasure. Like, how could you erase the content of the disk? Well, the UID is hard to change. But throw away the key, the KFS. And if you throw it away, you can't decrypt anywhere anymore from the file system. So erasure is not literally writing zeros to the file system. You can just throw away the key, right? And it's a very cheap operation. And so that's one way to do very quick erasure. Anyway, so almost a little bit of a side point. Then the file metadata, so like for every file, there's a little bit of metadata stored with it. And in that file metadata, is encrypted, using the KFS. And so the file system can like open it up, and then in that metadata for each file, there's a bunch of information. One, there's something that's called the data protection level. So this metadata is encrypted with this key KFS. The operating system doesn't have the key KFS, but can ask the enclave processor to please set up it so they can read the metadata. It reads the metadata. Inside of it finds the protection level. And inside of it also, and this data protection level, as we see in a second, produces different keys, or is tied to different keys. These are called the K data protection file keys. And the actual file system, the actual file key itself, is encrypted using that KDF. So for the operating system to be able to read a file, it needs that the KF. So somewhere in my, whatever is some file that I got stored here, that's encrypted using this KF. To be able to read it, I need to get access to the KF. The way to get the access to the KF, I need to get the KDF. And basically, the operating system has to go to the enclave processor and ask it basically, do you have KDF or a version of KDF? So that I can, find out what this KF is. And this intermediate step allows them to implement different key delegation schemes. So this KDFS is computed in different ways and depending on the protection of the file. So let me run through some of them. So the 4 protection levels. One is what is called complete. So that's number 1. And complete means that the KDF is derived from the user PIN code. And so that means when the phone is locked, the enclave processor doesn't even have that KDF because it doesn't have the PIN code, right? Because when the phone is locked, the PIN code is basically, the key that goes along with the user is completely erased. And so these files cannot be read or written when the phone is locked. And so background applications can't read or write those files. So that is the sort of the most secure version. Then then there's something that's called complete unless open. And this is for these background applications. That's basically a special constructed KDF by the enclave processor so that the application can write or append to files, but actually not read them. And so while the phone is locked, that particular key actually sits in the memory of the enclave processor. And so applications, or the file system can ask the enclave processor to stick that into the AES engine, and then basically read and write, or actually in this case only append or write data to those files. And this is basically the case. The poster child for this particular protection level is like email, where you want to download email messages from Apple and then write them into your file system. Then there's a third case, until first authenticated, until first authentication. So this is a KDF that is basically constructed the first time you type in your password. So you boot the phone, the secure processor has, computes a KDF in that particular case, and keeps that KDF around even when you lock the phone. And so files that are protected using, or have this protection level until first authentication, can still be read and written by iOS, even if your phone is locked. Okay, so your most precious data shouldn't go in there, correct? Because if the attacker may be able to get hold of that, if you can get hold of this KDF that still sits somewhere in the enclave memory. And this is actually, this key is generally intended for third-party application, or for the data for third-party applications. It's sort of like, similar to like, basically on-disk file encryption. There's at least, the file's always encrypted. Okay? So that's for third-party. And then the fourth level, basically, there's no protection other than actually encrypting with the file system key, the base file system key. Okay, does that make sense? So this background apps, correct, is such a challenge, correct, that there's a whole story about like this key chaining to actually make that work out correctly. Yeah?
What does KFS encrypt the whole file system, and then there's another level of encryption on top of it?
I think KFS encrypts the file system. That is the basic file system encryption key.
So then how does KF relate to that?
So KF basically store, I think the way to think about it is that the KFS is the sort of the block level encryption that the disk does periodically. And then on top of that, you can actually encrypt the files with KFF so that only if you have KFF you can read it. So there's multiple levels of encryption even going on. Good point. Okay, good. All make sense? Okay, so now let's step back a little bit and ask ourselves, how secure is this? And like, what is the remaining sort of attack surface? I'm going to get a new piece of chalk. Okay, so we already identified earlier on one of the issues here, correct? Apple's private key. Any other sort of remaining, or like, if you look at this design, you're an attacker, what are the places you could go after? Yeah.
Try to get someone to mistakenly put in their PIN?
Sure. Sort of phishing attacks. Trick a user basically to unlock the phone. Interesting. That seems like a total reasonable thing to do. Or for somebody, yeah. So.
If there's a way to read the UID, you could use that.
Yeah. Okay, so how could you read the UID? So certainly we should be worried about it, correct? Do we think that's hard? Yeah, there's a little bit of a mystery exactly how this works. Yeah? So I think the basic plan is like, the key is sort of fused into the silicon. And so that would mean you have to sort of slice open the silicon and have some super duper, microscope, to sort of read it. And supposedly this is a super expensive attack to pull off. Not impossible, apparently. I have no experience with this, so I don't really know. But this is, extreme stuff. Really, really, requires a lot of money to actually for an attacker to pull that attack off. Yeah.
Will it be to completely replace the ROM inside the enclave?
Sorry?
To like physically replace the ROM inside the enclave?
Yeah, I don't know. That presumably is also possible, or maybe not possible, but presumably very expensive too. I mean, you got to do it in a way that basically still the enclave chip works, right? And that might basically, sort of, I don't know exactly how it would work. You slice out the ROM, put the new ROM in, cover the whole thing back up, and apparently this is very, very difficult to do. I mean, the enclave processors are like temper resistant. You know, they designed it in a way to make those kind of attacks super difficult to pull off. Yeah.
Third-party apps, if they have access to certain APIs that they can sort of like meddle with the address. I know that there's like a random address layout, but still like it could be like good.
Yeah, so I think the classic case, which is probably actually the attack surface that's most used currently against iPhones, is like bugs in iOS, or in the driver software, or anywhere basically that in the software that actually is running on the main CPU. Why would it be good for an attacker to be able to get control over iOS? What could you do? I mean, wasn't the whole design set up in a way that basically all the sensitive computation happened anyway in the enclave processor? So what do you gain by actually having control over iOS? Yeah?
You can still access the sensors of the phone, for example, perhaps take images.
Yeah, well, actually, there's a much more fundamental problem, correct? When the file system runs here, correct, on the main CPU. So once an iOS app, wants to read your files, correct, it will ask, the enclave processor to set up the appropriate key, correct, here. And then, it will decrypt the data, and actually the data will be stored in memory, correct? So when the phone is unlocked and, you have control over iOS, you might be able to read, the user's data, right? Because it's going to be sitting unencrypted inside of the main memory. Does that make sense? And so, and this sort of like we talked a little bit about it, they don't really, they only protect really your data when the phone is locked, not when the phone is unlocked, because actually the iOS needs to have access to your data to actually run the applications. And so that's a profitable place to actually attack iPhones. Apparently quite hard. Does anybody know what the going market rate is for a zero-day exploit? There's a market in this. So if you want to buy one, you can actually do it. You need quite a bit of money. So turn out roughly, I think, in the order of $1 million to buy, go to some company that specializes in actually manufacturing zero-day exploits, and you can buy one. Apparently, in the last couple months, the price has gone down a little bit because there have been a series of bugs. But it's still roughly around $1 million to actually find those. Good. So presumably the other place you could go for is not only bugs in the iOS, but maybe bugs in booting. Okay, because if you could get a handle on the booting process, get your code inserted in there, then you could take control of the phone, right? Because then you can boot the software on it that you want to run, and then you're in good shape as an attacker. Okay, so to summarize, what we see here is a design, correct, where people took a step back and said, like, okay, let's try to tackle that particular threat model head on, and deployed quite a number of impressive machinery and engineering to achieve that, correct? And the attack surface is much more limited, much harder to exploit, and much better security than I think than your desktop or your laptop actually has. So it's quite impressive. Okay, we'll see on Wednesday how that plan sort of percolates up, to applications. All right? See you Wednesday.